Welcome back to Probability, and today we're going to be talking about moments. So, what are moments? Well, last time we talked about expected values. So, recall that the expected value of x, where x can take up k different values, is equal to the sum from I equals 1 to k of each of those values ni multiplied by the probability that x would be equal to ni. Alright, and this is actually written as the probability density function, p of ni, because, this analogy doesn't make much sense when you start generalizing it to another kind of variable that we'll look at later. So, we replace this with that. Now, you'll notice one critical similarity. But what is it? Okay, so I want to ask you something for a second. Let's say we have the real line. And on this line, there are a few masses. Mass number 1, mass number 2, mass number 3, 4, and so on. I'm not going to number them the same. And, of course, they all have different positions. And your question is, where is the center of mass? So the answer to that is instinctively xCm is equal to the sum of xi, mi, from I equals 1 to k, however many masses there are, divided by the sum, xCm is equal to the sum from I equals 1 to k, if k is the number of masses, of xi, mi, divided by the sum of mi by itself. Now, this already looks very similar once you consider that the probability density function is essentially kind of a mass function. I mean, you kind of call it a probability mass function half the time anyway. So this is sort of analogous to this, right? So is that all the connection? No, because the sum I equals 1 to k of the probability density xi is equal to 1 all the time. So if you actually think of this as just the probability density function, instead, since this is always going to be 1, this just simplifies to the expected value function. Do you see how the expected value is somehow equivalent to the center of mass? Okay, so that's pretty cool, right? But remember, just like the center of mass, let's say I have a gallon full of water. And that gallon is, full with water. So where's the center of mass of this object? Well, it's going to be right in the middle. But does that mean that the water in the middle is denser than every other part of the water? Is this any more dense than the water is at the bottom or at the top? No, right? So here, the center of mass is in the most dense part. The same way, and that sounds obvious, right? The same way, if I have an empty jug, so this one is full of nothing but air, the center of mass is still going to be smack dab in the middle. Well, maybe a little to this way because of the handle. But does that mean that this is the densest part of the object? Well, in fact, the plastic that lines the outsides is much more dense than wherever the center of mass lies. So, in some situations, the center of mass can be just as dense as any other part. And in some situations, the center of mass can be the least dense part of the object. Like if you have a hollowed out pumpkin or something. The same exact way, though it sounds a lot less intuitive, the expected value can be just as likely as any other value, or the expected value can be the least likely to happen. You see? So, here's one other thing I have to add, the main point of the lesson. Expected values are not the only thing you should judge a probability distribution by. Just like you can't judge a book by its cover, you can't judge a probability distribution by just its expected value. Let me ask you this. In one situation, you are offered a chance to gamble for $5. That's not how you draw money. Now, of course, $5 is not that much. You have a 50% chance of winning, let's say, and a 50% chance of losing. You're betting it all. Oh, Jesus Christ, I can't do this one cap's already in my hand.
That color is not good.
Yeah, it is. You're betting it all on one coin flip. So, if it lands on heads, then you get the $5. If it lands on tails, you're going to have to take $5 out of your wallet and give it to someone else. Alright, doesn't sound too bad, right? Most of you would take that offer. Now, let me give you a second offer. You are given $1 million if you have the guts to play Russian roulette. So, there's 2 chambers, and one of them is loaded with a bullet. So, would you take that offer? No, of course not. That's stupid. I mean, who would gamble with their life for just $1 million? But, now let's try to model these with probability distributions. So, let's call this x1, the relative value to you. So the probability that x1 is equal to 5, so you get $5, is 1. Sorry, I mean 0.5. And the probability that x1 is going to be equal to minus 5 is equal to 0.5. Since there's a chance you gain the $5, there's a chance you have to take out $5. Now here, you have a random variable x2. The probability x2 is equal to $1 million is 0.5. But the chance that you die is also 0.5. So, in this case, what's their expected values? Well, the expected value of this one is 5 times 0.5 plus minus 5 times 0.5, which is 0. The expected value of this is 5 times 0.5 plus minus 5 times 0.5. Which, 10 to the 6 plus minus 10 to the 6, which is also 0. So, are they the exact same offer? Does it make no sense to not choose the bullet, but choose the $5 gamble? Well, it does make sense. And the answer is it does make sense. And the reason is because there's more aspects to a probability distribution than just expected value. Enter the moment of inertia. Let's say I have a bowl, and inside this bowl is a little fish. Now, it takes me an extreme amount of work to rotate the entire bowl 360 degrees because it's like 50 kilograms and it's super dense everywhere. But the fish, rotating the fish around 360 degrees requires me to take it out, and I've already done it. The fish has probably died too. So, the bowl is a lot harder to rotate than the fish, even though both of their centers of mass are directly in the middle of this bowl. So, there's a second component, moment of inertia. And this is where the mind-blowing stuff comes in. Moment of inertia, its counterpart in probability is the standard deviation. Yeah, it sounds stupid, but it's true. The moment of inertia is all about, if I spread my hands out like this, I have a much higher moment of inertia than if I put them in like this. As you can see, I'm applying the same amount of torque with my feet to make me spin, and yet the moment of inertia when I have my arms spread out causes me to spin slower. So it's all about how far you have all your mass spread out. If it's all squished in like this or all spread out like that. In the same way, standard deviation is measuring how far the entire data set is, on average, from the expected value. So how do you measure that? Well, instead of this formula, the standard deviation is just this squared. That's where the standard deviation comes from. It's like the analog of the moment of inertia. And you can keep going. Just because two objects have the same mass, same moment of inertia, same center of mass, same moment of inertia, and just because two probability distributions have the same mean and the same variance doesn't mean that they are the same. To do that, you have to ensure that their third moment, the skew, is the same. And then, after that, you have to ensure that their fourth moment, the kurtosis, is the same.